Wade and Roy are the other two committee members. So we could get started, and if you take about an hour for your presentation, but don't go up beyond that if possible.
Okay.
And if you'd like to ask questions in between, that's fine, we can stop there.
Okay, hi everyone, welcome to my PhD thesis defense. The title of my thesis is Algorithms and Protocols that will improve spectrum utilization in future mobile networks. So during my PhD, I have worked on two main scopes. One is future mobile internet services, and the other one is dynamic spectrum management. Within the future mobile internet services scope, I started by looking at name-based communication and name-based network architectures with the focus on mobility first as a new paradigm for a name-based network architecture. Within Mobility First, I worked on two projects that are enabled by Mobility First. One is multi-network access in cellular networks, and the other one is ICN-enabled cellular multicast. And then I worked on an experimental wireless emulation platform on Orbit that will facilitate experimenting with these new protocols and comparing them with the existing protocols. Within the dynamic spectrum management, I started by looking at the coexistence of LTE and Wi-Fi in the unlicensed band and different methods that will enable their fair coexistence. And then I moved to looking at a distributed architecture for dynamic spectrum management. So in this talk, I'm mainly going to focus on these three topics: multi-network access in cellular networks, ICN-enabled cellular multicast, and the dynamic spectrum management architecture. So the outline of the talk is, firstly, I will motivate why we need to utilize spectrum more efficiently by looking at the evolution of mobile data and the new services. Then I will go over the three projects I have worked on to satisfy this goal of utilizing the spectrum efficiently, namely network-assisted multi-homing, ICN-enabled multicast, and dynamic spectrum management. So, as I mentioned, to motivate why we need to improve utilization of spectrum, we have to look at the two important trends in evolution of mobile traffic. One is the fact that there is still exponential growth in mobile data traffic. According to the new reports, the mobile data will increase by 5-fold by 2024, 25% of which is going to be carried by new generation of cellular networks. And also, in the past few years, there have been emergence of new services, each of which have their own latency and throughput requirements, ranging from ultra-low latency mobile experience, you must have all heard about AR/VR, mission critical services, and massive IoT. So, so all of these point to the fact that spectrum needs to be improved, spectrum utilization needs to be improved. And there already exist some proposals on the physical layer, new physical layer technologies to support this, and also on end-to-end applications and new transport layer protocols to support it. But in this thesis, we wanted to look at additional ways to improve the efficiency of spectrum utilization, mainly inside the network and using network protocols. So the first project that I have worked on looks at how we can stitch the capacity of multiple wireless networks together for simultaneous data delivery to a mobile device, which is called multi-homing. The second project, with again the goal of utilizing the spectrum efficiently, wants to send the same data using the same spectrum to multiple of mobile devices, which is wireless multicast. You can imagine this having use cases in vehicular to infrastructure communication, sending an upgrade to a number of IoT devices, venue broadcasting, or public safety scenarios. And the third project looks at how multiple wireless technologies can share the same spectrum in a dynamic and distributed way. As you see in this figure, there have emerged new paradigms for spectrum sharing, and we wanted to look at how all of these can be supported using a distributed spectrum management architecture. So how is this mobile data demand supported in today's internet? Well, for the first goal that I talked about, which is having advanced mobility services, an example of which is multi-homing. This is done in today's internet either on an end-to-end basis on hosted services and applications, which will take care of adaptation to last hop link quality, doing multipath data delivery, and name resolution services for content delivery and, for example, DNS services. Or a lot of the functionalities required to mobility are taken care of at the wireless access networks. For example, mobility management in cellular networks, QoS management, and more recently in 5G dual connectivity, which is taken care of at the wireless access network. For the advanced access services like cellular multicast, this is done through, this is again done at the wireless access networks, mainly in the cellular networks using new specialized entities and protocols. And spectrum management today is mostly done either at the access networks by doing local radio coordinations or just improving the radios to do sensing and backup, or it's done on a centralized spectrum management database, which acts as a repository for spectrum management. So in this thesis, we want to support all these functionalities inside the network, and the goal that we believe we will achieve by doing this is to reduce latency and overhead, having more dynamic adaptation to the varying wireless link quality, avoid having specialized hardware, infrastructure, and protocols at these cellular access networks, and having more dynamic and distributed control. So with this introduction, I will jump into the first project that I've worked on, which is network-assisted multi-homing. So as you know, a mobile phone is in the coverage area of multiple wireless networks at a time. And previous work has been done on showing that the throughput and different other quality of users' experience can be improved by receiving data simultaneously on, for example, Wi-Fi and cellular in heterogeneous scenarios. Our focus has been on enabling multi-homing for cellular networks, meaning that a device will receive data simultaneously using several cellular carriers, which will not only take advantage of the diversity of the wireless links and the core cellular networks, but also it challenges the existing cellular communication models. So how is it done in today's internet? In today's internet, connections are bound to legacy TCP/IP. So basically, whatever you want to do has to be done on top of that, and it's end-to-end. And the most widely used protocol which enables multi-interface connectivity is multipath TCP, which basically requires the receiver to directly inform the sender about the multiple interfaces that it's willing to receive data on, and then the sender will do the data splitting based on inferring the bandwidth of the links and by doing the per-subflow scheduling on an end-to-end basis. And the core network is mainly in charge of doing simple address-based forwarding. So we believe that these functionalities, if they are supported inside the network, there will be a lot of advantages in terms of the mobile user experience, which we show later. And as a candidate architecture that supports these functionalities inside the network, we took mobility first because of these three main features that it has. One is naming, where, so in mobility first, every device is assigned a globally unique identifier, which is independent of the device's point of attachment to the network, called the GUID. And then a name resolution service is needed to give the mapping of the names to addresses, called GNRS. And because the network elements are able to do name-based services, we can actually do the data splitting inside the network instead of doing it on an end-to-end basis. And different algorithms can be applied to do data splitting. In previous work, my colleague has shown how reliable hop-by-hop back pressure mechanism can be used for data splitting. In this work, we look at how a last hop link quality feedback can be used to do data splitting. So this is an overview, a protocol overview of network-assisted multi-homing. So once a UE gets attached to these access networks, the edge routers will keep a mapping of the GUID of the device with a history of the bitrate. Now this bitrate can be inferred based on the access protocols of Mobility First, or it can be directly obtained from the radios at the base stations. Once the sender wants to send the packet to GUIDR, the first hop router will look up the GNRS for GUIDR, and it will get the network addresses to which this GUIDR are connected to, and the network addresses will be appended to the packet. So throughout the network, the routers will just do address-based forwarding until it reaches a point that each of the network addresses have a different next hop. That will become the bifurcation router, which will request with the GUIDR for the bandwidth from the edge routers and gets a response back. And this can be done periodically. So this bifurcation router will do a weighted round-robin scheduling of the chunks for each of the subflows, and also in order to minimize out-of-order delivery at the receiver, it limits the transmission window for each of the subflows relative to the delay bandwidth product. So we implemented network-assisted multi-homing in NS3 in addition to all the existing modules, and some modifications were needed, for example, for a single UE to be able to attach to multiple cellular networks. And then we compared it with the Linux kernel implementation of multipass TCP using direct code execution, and we evaluated the performance of network-assisted multi-homing compared with multipass TCP using some real-world traces. So the traces, because we wanted to have a we wanted to have an understanding of how two different carriers' signal strength are at the same location. We took two phones and we wrote this application that logs different measurements. What we looked at was the RSSI values for two different carriers, and we collected these RSSI measurements over 10 days, and in the end we used 217 minutes of these measurements. And since Ivan is here, this is the route from Milad to his house. This is a sample of the measurements for these two different carriers for the RSSI measurements. Then we fed these RSSI measurements into the physical layer module of LTE in NS3, and we looked at the retrieval of the large file to compare the download performance for network-assisted multi-homing, multipass TCP using the best interface by using Mobility First architecture, and single TCP over each of the cellular carriers. So in this plot, we are showing the average throughput. As you can see, network-assisted multi-homing is able to achieve 1.9 times more than the average of the single TCP values, while multipass TCP is only able to achieve 1.4 times more. And this plot shows the average throughput versus the average delay. Each dot in the plot shows one of the traces that we used. So again, as you can see, not only network-assisted multi-homing not only it improves the average throughput, it reduced the average latency the packets experience as well by 2.3 times. So we believe this is mainly because network-assisted multi-homing, because we are doing the data splitting inside the network and also limiting the subflow, each of the subflow's transmission windows to the delay bandwidth product, we are able to, we have a more updated information about how the link quality at the edges to do the data splitting compared with multipass TCP, which does this on an end-to-end basis. So in order to confirm this, we took one of the traces and just increased this in-network delay in the steps of 5 milliseconds from 1 to 50. because we wanted to show that multipass, as this in-network delay increases, multipass TCP is actually unable to adapt to the link quality worse compared to network-assisted multi-homing. As can be seen, the throughput for network-assisted multi-homing doesn't decrease that much with this delay increasing, while the throughput for multipass TCP decreases greatly, which again is mainly due to the disability of multipass TCP to adapt to the wireless link quality. So in summary, we propose multi-network access for in cellular networks to improve throughput and reduce latency. We showed that network-assisted protocols perform better compared to end-to-end transport layer protocols. And through trace-driven simulations, we showed how network-assisted multi-homing, its performance is better. Other work I have done for this project was to experimentally evaluate multi-homing in mobility first compared with multipass TCP on orbit testbed using the mobility first prototype that we have. And also we looked at how multi-homing can be done in, how it is done in next generation cellular networks, mainly for the dual connectivity mode in 5G, and how having a flat mobile core architecture will improve the performance of multi-homing. But I haven't included these in the slides. So the next project I have worked on is ICN-enabled cellular multicast. So as we know, multicast has been shown very effective in data delivery in the core network by reducing the overhead and improving the throughput, reducing the load in the network and improving the throughput. And there has been efforts to support multicast at the access as well in the cellular networks. And mainly cellular multicast has evolved in two paths. One is a mixed mode multicast where within the frame or subframe there is dynamic switching between unicast and multicast flows. And the use cases that this can support is, as I mentioned, sending, for example, a software upgrade to a number of IoT devices, vehicular to infrastructure communication for public safety, and for example, venue broadcasting, where in a congested stadium, a lot of people want to receive a live video of a specific scene of the game. The other path, which we're not going to focus on, is having a dedicated broadcasting network for digital TV, which is not the focus of this work. So as I mentioned, cellular multicast has been proposed in current LTE networks, and it started in release 9 of 3GPP by the standard called Evolved Multimedia Broadcast and Multicast Service, or EMBMS, which basically is based on adding new entities and new specialized protocols to the existing cellular architecture. So the new entities which were added to the existing cellular architecture is this entity called BMSC, which is an interface between the content provider and the core cellular network, a specific gateway called MBMS gateway for the multicast data, which can have IP multicast to the EMBs in the network, and the coordination entity called MCE, which basically makes a lot of configuration decisions and has to send this information to the EMBs for configuration of multicast data delivery. The newest standard, which has tried to address a lot of problems in the older standards, which was static configuration of multicast delivery, is called a single cell point to multipoint, which is the focus of our work, which allows for dynamic multiplexing of unicast data and multicast data in the same subframe. So now I'm going to talk about our solution for a cellular multicast, and then I will compare our solution with the existing standard, which is called SCPTM. So our idea was how we can use identifiers and ICN semantics at the base stations, basically to be able to mark a number of resource blocks for a number of UEs which want to receive multicast data. So as I mentioned, in the core network, this has been taken care of before, And what we are interested in, once these UEs have subscribed to a specific multicast service with IDM, once that data reaches the base station, how can the base station, by keeping a local mapping table of this IDM and the UEs which have subscribed to this UE, can use this information in its MAC scheduling to enable dynamic multicast without the need of all those specialized entities and protocols. So this is not really the focus of my work, but I just wanted to mention that there are two important features in Mobility First that enable efficient data delivery for multicast data up to the base station. One is the flat cellular architecture, and the other one is the pop-sub systems in Mobility First, which basically takes advantage of recursive lookup and encapsulations, which I'm not going to the details of. But our contribution is mostly on the access protocols for IMAC, and here is the comparison of the access protocol for SCPTM and IMAC. So first we focus on SCPTM. When multicast data reaches the cellular network, a number of control messages need to be exchanged for the tunnels to be set up for the data to reach the EMB. Again, our previous work has shown that these control messages actually induce a lot of overhead and latency, initial overhead and latency for data to arrive to the EMB. And then once the data gets to the EMB, in SCPTM, a periodic announcement is used to let these UEs know about the specific configurations which are needed for SCPTM. So in cellular networks, usually what happens is UEs turn off their radio chain and they only wake up at predetermined times, which is their DRX cycles, to see that if there is any data for them or not. The problem here is that these UEs which have subscribed to this SCPTM service have to wake up at these periodic SCPTM announcements in addition to their DRX cycles. So there is so this will cause battery usage, increase the battery usage on the UEs. So there needs to be a trade-off between how frequently you're going to send this periodic announcement and how much battery usage the UEs are able to tolerate. Imagine these UEs are IoT devices, then this periodic announcement cannot be that frequent. So in SCPTM, in IMAC, what we can do, because of the local mapping table we are keeping at the base station, is that we can reuse the existing attach process in LTE to let all the UEs know that they can use the same identifier. Now I will go into the details of this in the next slide, but the main idea is that every UE which wants to receive this multicast data will be paged individually, and then in the attach process, all the UEs will be given the same configuration to be able to receive the multicast data in the next frames. So the way scheduling of data is done in LTE in general is that all the UEs need to have a specific identifier called RNTI to be able to decode the control part of the message. And once they decode the control part of the message, they will be able to decode the data part of the message, because the control part includes important information like modulation encoding scheme and resource block assignments and etc. So all the UEs which want to receive this periodic announcement for SCPTM need to have this SCRNTI, which is given to them in the system information. And then once they decode this periodic announcement, they will find this mapping of the multicast service identifier, which is called TMGI, to something called GRNTI, which later the LT architecture will use to mark the multicast data with the GRNTI. But in IMAC, because we are keeping this local mapping table of the ID of the multicast service to the ID of the users, we don't need to let the users know about this RNTI, which is gonna mark the multicast data periodically. We can just use one RNTI for all of the UEs, which we call iRNTI here, to send the multicast data on. So later I will talk about what exact advantages this has compared to SCPTM. So because both SCPTM and IMAC enable a multiplexing of unicast and multicast data within the same subframe, we need to first look at the problem of resource allocation. Resource allocation problem mainly wants to determine the number of resource blocks which are going to be assigned to a flow, and the modulation and coding scheme used, which determines the number of bits which are going to be sent on each resource block. So for multicast flows, what the MCS we will choose is the minimum of the MCS of all the UEs in a multicast session, because we want to maintain the low bit error rate. And you can see that grouping of UEs will be useful here based on the objective of the resource allocation. So here y, the parameter y determines the number of resource blocks assigned for the unicast users, and x determines the number of resource blocks for the multicast users. So first we look at the problem for resource allocation. We consider a common metric called proportional fair metric. And the first problem we look at is long-term resource allocation. A very common objective function to maximize when we want to achieve proportional fairness is maximizing the sum of the log of the throughput, and that is the first equation here. Rn is the throughput for the unicast UEs, Rmk is the throughput for group K of multicast session M, and Gmk determines the number of users in group K of multicast session M. So we basically want to maximize the sum of the log of throughput for unicast and multicast. The first constraint just basically wants to ensure that the number of resource blocks assigned to unicast and multicast users is less than the total number of resource blocks which LTE has. The last two constraints are about grouping. This one makes sure that there is no overlap among the different groupings of the multicast session, and this one makes sure that with our grouping we cover all the multicast UEs. So given if we consider the groupings to be fixed, this is a convex problem, and the solution of it is kind of intuitive, that for each unicast session, it will get 1 over the total number of multicast UEs and unicast UEs, and for each multicast session we get the same as the unicast session times the number of UEs in that group of that multicast session. So that was the long-term resource allocation problem, but in real systems what we need to do is we need to assign resources every time transmission interval, or TTI, because because of the mobility of the users and the channel conditions changing, the MCS value changes. And also the convex problem we looked at give optimal solutions as fractional values, which cannot be used on a per TTI basis. I mean, they can be used, but they're not guaranteed to give the maximum proportional fair utility function that we are interested in. So, so we are here looking at the integer programming problem. But in order to use the common solvers which exist for integer programming, we wanted to make the objective function linear, and a common approximation for the PF utility function is to approximate the log of the throughput with the ratio of the instantaneous rate over the average rate throughput. So this shows a reformulation of the previous objective function by considering this approximation of the PF utility. And then we do a change of variables to use the binary variable, which is RBIK, which basically determines whether resource block B is assigned to group K of flow I. And this constraint makes sure that each resource block is only assigned to a multicast session or a unicast UE. And these are the same, these grouping constraints are the same as before. So, so far we have considered that the groupings are fixed. Now we want to look at how many different groupings do we actually need to consider. each color in this figure shows a different MCS value for the UEs. So if you want to enumerate all the different groupings, that will be a very big number. It will be the multiply of the Bell number for the number of UEs subscribed to a specific multicast session. It has been shown in previous work that an optimal solution exists if we just sort the UEs and consider the groupings by partitioning this sorted sort the UEs based on their MCS values and consider this order grouping. In our work, we have shown that, and this is kind of intuitive, but we have proved that if we actually put all the UEs with the same MCS value in one group, the utility, the proportional fair utility function will always be higher than if we separate the UEs with the same MCS into different groups.
So they all want the same content.
Yeah,
right?
yeah.
But like somehow you're going to give those two guys who have like the best channel, the MCS3 guys.
Yeah.
Like you're gonna give them you're gonna give them a different stream with this better rate.
Yes, yeah.
So isn't sometimes the solution to be like, no, just lump them in with the MCS2 people?
So we check all the different groupings, but the number of groupings we check is only considering all the groups with grouping all, we sort all the UEs and only consider the partitions between groups with the same UEs with the same MCS in the same group. Not same UEs, the UEs with the same MCS in one group.
So do you consider like giving the people who can get MCS3, giving them just MCS2 service?
Yes, yeah. So if we put these two groups together, then we have to reduce the MCS to the minimum of the MCS of the group. And then we solve this optimization, we find the maximum value of it, and among all the groupings, we pick the maximum value.
Somehow your solution doesn't allow you to be like, oh, these guys have a lousy channel, we're just going to throw them away.
Actually, that's what I saw that will happen. So the solution to the optimization, so there's going to be a trade-off, because the more number of UEs you have in your group, the more number of resource blocks you're going to get based on the solution to the convex problem. So, but at the same time, if you have a UE that has a small MCS, you're better off kicking that UE out of your group. So this trade-off exists, and I have shown, I don't think I have the results here, but in the thesis I have shown how on average, for example, for 400 TTIs that we run this optimization, how three of the UEs with the lowest MCS on average are going to be left out a lot of times. But because of that, that's good, because you can also think that if this trade-off didn't exist, you can also think that, okay, we always just pick the maximum MCS UE and forget about all the other UEs. But because of this trade-off that the multicast service is getting resource blocks relative to the number of UEs it's going to serve, it's ensured that at least a fair number of UEs will get the multicast throughput. And we have also talked about how those left out UEs can receive the multicast data through mechanisms like D2D and
so if I have a layered encoding scheme, how does it interact with this kind of, we have resource allocation, right? Can I selectively take subbands and serve disadvantaged users with the lower subband, and the higher ones get larger number of subbands, right? If I have that kind of content encoding, how does it?
I'm not that familiar with the physical layer, like layered encoding schemes. I think Pedro was looking into a lot of these aspects when he was working on the video.
Because here you are not assuming any assistance from the coding layer, right? The coding layer is one flat, everybody gets the same but at a different modulation.
Yes, just
format,
a different modulation, yes, yeah. Different like number of bits per resource blocks. But maybe if you elaborate on your question.
Yeah, so my question, maybe I don't want to take up time in this session, maybe we'll go to the next one. The idea is that if I have a disadvantaged person, rather than giving him the full post dump, I give him a smaller portion of the code at a lower rate, and he's still able to sustain.
Actually, that is implicit in this formulation. That is the logarithmic, the utility function in the log means that you have to have a source coding scheme which kind of follows the log relative to most source coding has that kind of a shape, and that's why we formulate, but she didn't look into a specific one. But in principle, the lowest MCS guy will have to send something useful. If that's video, then you have to drop your rate.
I think the question you're asking is somebody else's thesis. The thesis, right? Like this question of, oh, if you do some kind of superposition incremental coding, that the person who get MCS2 gets you don't have to, you only really have to do the incremental, you know.
Precisely, and
Yeah.
it's almost like I was trying to get the underlying assumption on how the content is encoded from her, I think so. Yeah, so you're not assuming any specific assistance from the coding layer.
No.
So does the
Yeah,
person
yeah.
getting MCS1 get exactly the same content ultimately as the person getting MCS2?
Yeah.
So,
But we are coding everything with MCS1. So the person that has MCS2 could have gotten like high, but the other thing is, that's what I'm saying, now that you have two UEs in the multicast group, it actually causes the number of resource blocks which is going to be assigned to the multicast flow to be twice as well. So you're having more resource blocks, but that is dictated by the minimum of the FCS of the UEs in the group. Should I continue?
yeah.
Okay, so we wanted to evaluate how this per TTI resource allocation compares with the solution to the convex problem that we saw earlier. Obviously, we wanted to look at the average performance of the per TTI results. So in order to have input, these MCS values as input to be meaningful, because these information are not usually available because the MCS values are decided by the base station. But what we did is we synthetically generated MCS values with NS3 for 400 TTIs, and we looked at changing the total number of UEs and the percentage of the UEs which are subscribed to the multicast, to one multicast session. So here first, by looking at the red plot, which shows the sum of the unicast throughput, we, based on the solution to the convex problem, this sum should only be relative to multicast percentage and not relative to the number of UEs, which the trend is maintained here. As you can see, when the percentage of unicast UEs drops to 50%, the total throughput also drops to 50%. And for the multicast throughput, again, if we went back and looked at the convex problem solution, what we are showing here is the aggregated multicast throughput, which means that we are multiplying the throughput of a multicast flow by the number of UEs which will receive this multicast data. So based on the convex solution, that should be relative to NP square, P being the x-axis here, and we can show that this is actually maintained for the average throughputs of the per TTI resource allocation algorithm.
What's the typical TTI in LTE?
It's 1 millisecond, but so now for 5G, they're actually considering microsecond, like 200 microsecond, 125 or 250 microsecond. And for that to do, actually there was a recent paper in Mobicon this year on how to use GPUs to do resource allocation per TTI, because you need to solve this integer programming problem.
Precisely, I wanted to understand, when you're doing it in the simulation, how long was it taking out in the CPU?
1 millisecond.
You were able to do
But we are not here, this is not a, so we are, to solve the optimization, we are not doing that in NS3. We are just taking input from NS3 and then running the optimization, offline. So it's not like packet level simulation here.
How sensitive is it to the number of UEs, the runtime?
Runtime? I did a lot of these on the math server here, so I just let them run and like later check the results. So, I don't exactly remember. But so the different groupings that we are considering is 2 to the power of number of MCS values at max. That's how many groups we're going to consider. So it doesn't matter if the number of UEs is more than the total number of MCS values which can be used, then it doesn't matter. So next we look at the impact of grouping. Now this is one of the times that this is one of the features that SCPTM actually cannot support, because SCPTM is only giving one GRNTI to all the UEs which are subscribed to a specific multicast session. But in IMAC we can't, because we're giving UEs individually RNTIs. To receive the multicast data, we can just give different groups of UEs different RNTIs. So we wanted to show what is the ratio of the sum of the throughput for the optimized grouping compared with if we put all the UEs in the multicast session in one group. And we are considering 40 UEs and changing the percentage of the multicast UEs within these 40 UEs. So intuitively, as the percentage of multicast UEs increases, we expect, because the variation in the MCS values of all the UEs also increases, we expect the gains from grouping to be higher. And this is actually shown in this trend here, except for this one, for the 20%, we don't see like a linear increase. When I looked into this later, I saw that the standard deviation of the MCS values for this 20% scenario was actually the lowest among all the different percentages. So that's why the gain from the grouping is not, still it's optimized grouping is giving higher throughput, but the gains are not the same as the other ones. So in the end, I'm just going to show one multicast use case, which is for context-based service, which can inherently be supported with IMAC but cannot be supported with SCPTM. So here we are considering a use case which aggregates dynamic requests to join an ongoing data session. An example of which can be for these self-driving cars. When they're reaching a turn of a highway, they might want to join an ongoing live video session of the upcoming traffic. So this can, so with using IMAC, all of these cars which join this, which want to join this live video stream can be served using the same number of resource blocks, whereas in legacy cellular networks, all of these new requests will be served using separate unicast flows. So here we are considering 50% of the total UEs to request the same data, and the background traffic for each of the unicast flows is 2 Mbps, and this live video stream we consider it to be 5 Mbps. So when this plot is showing the sum of average throughput, again we are showing here the aggregated throughput, which basically multiplies this, for example, 5 Mbps by the number of UEs which are receiving it. And here we are showing what percentage of these requests for this 5 Mbps flow can be satisfied. So when we are at a small number of UEs, like 10 UEs, we are operating below the capacity of the system. So both IMAC and legacy cellular networks, both of them can gain the same throughput, and basically both of them are actually serving all the requests which are at the base station. But as the total number of UEs increase, we reach the capacity of the system. So and basically the percentage of these request to join this ongoing live stream is going to decrease because also the background traffic is increasing. But in IMAC, because we are basically, here we are looking at 50% of UEs being multicast. So basically 50% of resource blocks at the EMBR is going to be assigned for the multicast transmission. Even with 60 UEs, we still haven't reached the capacity of the system, and all of these requests can be served using the same resource blocks, basically. So in summary, we proposed IMAC, which can inherently support a lot of dynamic multicast scenarios. We proposed the per-TTI resource allocation algorithm that can be used for IMAC, and we showed the performance gains that we can gain using IMAC compared to SCPTM or just legacy cellular unicast for a specific context-based service. Next, I'm going to talk about the last project that I've worked on, which is architecture, dynamic architecture for spectrum management, distributed architecture. So this introductory material I've talked mostly about before, but again to recap, as I mentioned, there are with the 5G coming, there have been new spectrum sharing paradigms introduced and new wireless technologies that are going to be suitable for different sharing paradigms at different frequencies. And also there is the exponential growth in mobile data that will lead to demand for more and more wireless capacity and better coverage. And there are a lot of advances in the spectrum markets and regulatory policies. We believe that to satisfy all of these, a distributed spectrum management architecture is needed, and that's why we're proposing architecture called SMAP to support these requirements. So SMAP has a hierarchical architecture. On the lowest level, which is the radio control level, we have the radio devices and the base stations, a group of which are controlled by the mid-level wireless domain control. Each of these wireless domain controllers can be thought of as a software-defined entity that have extensions to support radio-specific parameters. And they are in charge of doing some optimizations and doing spectrum assignment to the radio control level by this interface using protocols similar to what is shown here. And on the highest level, you can think of the cloud services, which have a more global view of the network and can act as a spectrum repository, like policy repository, and also a spectrum aggregator or brokers, and enforcing different policies on the wireless domain control. Also, I have to mention that within these controllers, there needs to be two interfaces. One is for just exchange of the aggregated radio information or radio map, and also a policy interface, which has not really been the focus of this work, to do policy negotiations. As I mentioned, on the mid-level, we have the wireless domain level, and that can essentially create a connectivity graph with each of the vertices in the graph being a wireless domain controller, and the vertices having an edge if there is a need for these controllers to coordinate with each other, maybe because they have overlaps in their wireless coverage or some policy requirements. So having this architecture, different classes of distributed algorithms for spectrum management can be realized. One class is local neighbor exchange, where all the nodes will just simultaneously do spectrum assignment, and then they broadcast the information to their neighbors, and the neighbors take actions based on the received information from other controllers. The second one, which is the focus of the work I have done, is regional network optimization, or RNO algorithms, in which some information about the connectivity graph, structure of the graph is needed, and also the controllers will have unique identifiers to be able to run distributed algorithms with some help about the structure of the graph. And on the highest level, there is the logically centralized optimization, which can be done at the cloud service layer by running a global optimization and then assigning resources to the WD controllers. Also, as I mentioned, different spectrum policy can be realized using the SMAP architecture. This is mostly the contribution of our colleague, Professor Layer at MIT, and I'm not going to go into the details of it, just wanted to mention. In this work, we looked at one sample RNO algorithm. So I have to give a disclaimer here that there has been a lot of work in, for example, game theory field that looked at how to do distributed resource assignment in a way that Pareto optimality is reached. There's a lot of theoretical work on that. So the goal of our work is not on finding the best distributed algorithm, but mainly to take a sample distributed RNO algorithm, show its feasibility doing some experiments, and show some of the performance metrics. And the goal is basically to show that SMAP architecture can enable these kinds of algorithms. Yeah. So the sample RNO algorithm that we looked at has the goal of doing conflict-free resource assignment in the graph. What I mean by conflict-free is that for each node and its neighbors at a time, only one of them is active to do resource assignment. So this algorithm has as I mentioned, which is for all the RNO algorithms, it has a bootstrapping phase, which basically each node in the graph that has a unique identifier will let its neighbors know about its degree. So each neighbor knows the degree in the graph of its neighbors. And at every step, the node that has the highest degree among its neighbor that has not been optimized yet will be the master node, and it will run a local optimization to assign some parameters like frequency, time, or power. And then it will send an update message to its neighbors, including its own ID, the number of the lower index neighbors that this has, and a list of the lower index neighbors. And also the aggregated radial map information, which includes the optimized parameters that the master node had as a result of its optimization. Once the slave nodes receive this update message, they see that whether this list contains any common controller with a higher index that has not run the optimization yet. If that is the case, it means that this slave node has to wait to receive the update message from those nodes as well. Otherwise, this node at this super step, as we call it, will become a master node. Now, I know this is a bit confusing, so to make it more clear, I show an example here of the steps this distributed algorithm takes for a 6-node graph. So, as I mentioned in the first step, C4 here, for example, has the highest degree and the highest index in the graph, so it will be the first node to run the optimization. Then it will let all its neighbors know about its, using the update message, about its optimized parameters. Then only C3 and C6 will become active because, for example, C5 here, although it received an update message, it knows that C4 and it knows that C5 has a neighbor, which is C6, which has a higher index, so it has to wait to receive an update message from C6. So as you see, the algorithm goes on for 4 super steps until all the nodes have run their local optimization at least once. So to show the feasibility of algorithm like this, we did experiments on the sandbox 4 in orbit, using 2 sample experiments to do fully distributed channel assignment and distributed channel assignment for all devices LTE and Wi-Fi. So in Sandbox 4, we have a number of nodes that have Wi-Fi devices, and also I use 2 USRP nodes and run open air interface on them, which is an open source software that you can run in the unlicensed band. And also there is an attenuation matrix on SB4. All of these radio ports are connected to it. That allows for a 60 dB of attenuation, which basically will enable you to create different wireless topologies and do different experiments on them. So this is a topology I use for Wi-Fi, and this is for the LTE Wi-Fi. So the first experiment I did was a fully distributed channel assignment. So here we are considering 6 WD controllers, and each of the controller basically has 1 Wi-Fi AP and 1 Wi-Fi station. And I have shown the partial order execution of the RNO algorithm before. As I shown before, C4 first does its channel assignment, and then C3 and C6, and then C5 and C2, and then C1. As can be seen, after 4 steps of the algorithm, all of the nodes are able to achieve their maximum throughput. So the second experiment I did was for LTE Wi-Fi coexistence. So here we consider two WDs. One has 3 Wi-Fi access point and stations, and the other one has 2 Wi-Fi access point and station, and 1 LTE base station with LTE UE. So in the beginning, when they each WD does its channel assignment, because they don't have information about this overlapping edge overlapping at the coverage edge. The LTE base station in the unlicensed band is basically killing the Wi-Fi throughput completely. Once WD2 give its optimized parameters to WD1 and WD1 rerun its optimization based on this information, all of we can avoid the starvation of Wi-Fi node C3 while maintaining the same throughput for all the other nodes. So the last experiment I did was to show how a simple local policy can be realized in the same fully distributed channel assignment experiment. So here, for a public safety scenario, we are considering that some WD controllers have priority access to channels. Here, we are considering C3 and C4 having access to all the 3 channels, 3 non-overlapping channels that exist, while the other nodes only have access to 2 channels. This can be, as I mentioned, by blacklisting some of the channels on these nodes because they're not part of the public safety network. So again, the algorithm can run while it ensures that C6 here, which before it was using channel 3, will not be using channel 3, and the throughputs are again like higher than before while maintaining this local policy. So in the end, I looked at some large. Now this is not experiments anymore, but I just did numerical analysis of this sample RNO algorithm to look into a few performance metrics for it. One was the scalability of this RNO algorithm. So I wanted to, by scalability, I mean that how many super steps it takes for every vertex of the graph to do the spectrum assignment once only. And we looked at different graph sizes and changed the degree of the graph. As you see, the number of super steps increases logarithmically by the graph size, and even for a high average degree graph, including which is degree equal to 10, it only takes 16 steps for all the nodes to at least do spectrum assignment once. Next, we looked at the performance of the RNO algorithm for considering a specific policy that I will explain. For this, we picked actual Wi-Fi access point locations that we got from an open source data set in San Francisco, and we created a connectivity graph by aggregating the APs which were in a 200 meter by 200 meter area into one WD controller, and if at the same time, if there were more than 20 APs in an area, we divided them further to the WD controllers. Now, these numbers are just assumptions, and obviously based on how powerful the controllers are in terms of doing the computation.
How did you find the interference relationship between the APs? Distance-based?
Yes, distance-based. Yeah. So we considered the problem of channel assignment. Here, we consider that every vertex has a load, and we are measuring load by the number of unshared channels that the vertex will need. And we pick it uniformly from 1 to L, and then we vary L from 1 to the maximum number of channels, which here we are considering maximum number of 20 channels. So we wanted to compare two algorithms. One is that I call non-cooperative, is an algorithm that every WD controller will use all the channels. And the other one, which is fully cooperative RNO, is the RNO algorithm I talked about, but at the receipt of the update message from the neighbors, the node will not use the channels that its neighbor is telling it that it's using. So it's basically trying to do interference avoidance. So as you see, as the load increases, we are showing here what is the percentage of total nodes that can fully serve this load on them. So obviously, as the load increases, both of them are able to, there are less number of nodes that can serve the full load on them, but the fully cooperative RNO does 20%, close to 20% better for all the loads compared to just using all the channels in all the WTs. Also, to find this value for the non-cooperative case, we use the maximum independence set model to find a channel share, because for the fully cooperative one, the nodes, like neighboring nodes, are not really using the same channels, so we didn't need to. So in summary, we proposed SMAP, which is a distributed control plane architecture for spectrum management. We showed the feasibility of it using some experimental results for an RNO algorithm on the orbit testbed, and we showed some large-scale analysis of the scalability and performance of this RNO algorithm. So I think I'm on time. So in conclusion, my thesis focused on algorithms and protocols to utilize spectrum more efficiently. We proposed to achieve this, we proposed network-assisted multi-homing in cellular networks that basically allows in-network data splitting, and we showed the superior performance of it compared to end-to-end protocols. And we believe this challenges existing cellular data delivery models. Next, we showed how the use of identifier at the cellular MAC scheduling can alleviate the need for specialized protocols and entities to support cellular multicast. And we showed how this also allows inherent aggregation of requests for context-based services. In the end, we talked about architecture for distributed spectrum management that allows for distributed control and autonomy and can enable different classes of algorithms and different policies. So looking ahead, throughout my PhD, we worked with some IETF standards that were trying to promote the concept of name-based architecture for supporting mobile services more efficiently. There is an ongoing work in the IEEE standards, like as an example, IEEE 1905-2, which is trying to model spectrum consumption for different wireless technology, find a technology agnostic way to do it. So, and then that is going to be further standardized for policy negotiation and different algorithms. And also, although a lot of the proposals in this thesis might seem far-fetched and they're challenging the existing architecture of the networks and cellular networks, but two important trends of softwareization, this should be an and, softwareization and virtualization that is happening in future mobile networks like 5G will hopefully pave the way for incremental deployment of these solutions. So this is a publication list, and before we go into more questions, this is my favorite part of my slides. I wanted to thank my advisor, Professor Ray, for not only being the best advisor I can ask for, but also being a life role model for me. I wanted to thank my committee member, Professor Yates, Professor Trappi, Professor Mandaya, who was on my proposal committee, and Dr. Budikot for taking the time and also for their useful suggestions. Okay, Ivan is not here, but I wanted to thank him for his door always being open for the millions of questions I have asked him, most of which were stupid. I wanted to thank my family for their endless love and support. I wanted to thank my lab mates, a lot of which are not here, have already graduated. But if it wasn't for you guys, I would have graduated 2 years ago. You made the experience of being here very pleasant. And I want to thank my friends without whom I wouldn't have survived the past 5-6 years. And thank you. Yeah, I had to include them. These are 3 dogs in the lab.
They're your dogs?
No, but someone in the lab has had them for the past 3 years. So.
Yeah.
Yeah.
Ivan will say that. can't use his dogs in slides.
Oh, I already talked to Natalie. I got her permission to use it.
Okay,
Yeah.
so do we have any questions from the audience before we go into the closed session?
Come on, ask questions.
Looks like we don't have any questions now, so that's fine, and we can end this session, the public session, and then we'll go into well. Thank you.
Thank you.
Okay, so please go ahead with your questions.
Can we go back to the discussion on MBMS? So like, MBMS was around when I was a kid, so it's a classic area. So in your work,